Hello everybody! So today we're going to figure out the efficiency of a hot plate and how well it can actually heat up different materials. And we're going to focus on water and ice. So over here I have a beaker full of snow. I went outside and got some snow, and what I did is I measured the mass of the snow with this scale here. You can see that the snow is 58 grams. I tared the scale with the beaker in it, so now it's just reading the mass of the snow. What I'm going to do then is I'm going to take that snow and I'm going to put it on a hot plate. I'm going to turn the hot plate on. As I do that, I'm going to put this temperature probe into the snow. And over here, it's going to read the temperature very precisely for me in degrees Celsius over time. You can see right now the temperature is 0.7 degrees Celsius, which makes sense. It's pretty close to zero because the freezing point of water is 0 degrees Celsius. So now what I'm going to do is I'm going to turn on the hot plate and just kind of let this sit for a while and see what happens to the temperature as this thing heats up. So we'll turn on. Dun 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 dun. Ice, ice, baby. Dun 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 dun. Ice, ice, baby. Dun 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 dun. Specific heat. That's what it's all about. No, it's latent heat. Maybe that's what it's all about. I don't know the words. I'm just making it up as I go. But ice, ice, baby. Dun 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 dun. Ice, ice, baby. Dun 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 dun. Now it's water, water, baby. Dun 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 dun. Now it's steam, steam, baby. Dun 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 dun. Dun 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 dun. Dun 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 dun. Now, as you can see, the general shape of the graph, it's flat, then it's linear, then it's flat again. And here's what's going on. I'm going to talk about that in good detail. I also ran this simulation for 1,000 seconds, but I sped it up for you. We're going to make one more measurement before we talk about the analysis. Now, the hot plate gets its energy from electricity. So what I did was I hooked up a kilowatt meter up to the cord of the hot plate. And so what I'm going to do is I'm going to show you what that reads. Right here, it's reading the voltage. Hopefully you can see that. Reading the voltage. I'm going to switch it to the current. Here's the current. 1.97 amps. And the voltage, because it's coming on an outlet, 120.8. So the hot plate is using 120.8 volts and 1.97 amps. So that's its input current and input voltage. Now we're going to use that to try to figure out the efficiency of this hot plate. As you can see, the very first section here, from here to here, from 0 seconds on to about 240 seconds, the phase was ice. It was a solid phase. It was solid. Then from 240 seconds to about 754 seconds, it was water and it was heating up at a constant linear rate, meaning that the temperature was increasing as time went on. And then the remaining of the time, the 740 seconds to 1,000 seconds, it was boiling, meaning it was changing from water into steam. And this first part and this last part are latent heat. Those are phase changes, whereas this is specific heat, meaning it's just changing temperature. So specific heat changes temperature, latent heat changes phase. Okay, so I kind of drew the general shape of that graph so it's larger for you and so you can see those numbers better. So this first part of the graph, it was flat, meaning that heat was added to the snow, but it wasn't changing temperature very much. Now, if you look back at the graph, you probably noticed there was some bumps and stuff and some little it wasn't perfectly flat. And that's because that I had to move the temperature probe around so it was getting right in the snow. Some parts of it were touching the glass, or some parts were like the water was melting at different rates at different parts because some parts were ice, some parts were water. But in general, this is what the shape should be. It should be flat because the temperature does not change if it's changing phase. Since it started as a solid phase and went to liquid phase, that takes heat. That takes a certain amount of energy to go through that transformation. So that's called latent heat. Phase changes are called latent heat. So the temperature shouldn't change. But then once all the ice melted, then the water could start heating up. It went from 0 degrees Celsius about to 100 degrees Celsius about. Now those temperatures were pretty close. It's like zero point 0.7 to like 99 point something. And that's just uncertainty in the measurements. It should be 0 to 100 degrees Celsius. And that's pretty linear. If you look back at the graph, it's pretty linear. And that part of it is called specific heat. Specific heat means a temperature is changing. Heat's added, and it's actually changing the temperature or the kinetic energy of the molecules involved. So water is heating up in this section. Then, once it reached that 100 degrees Celsius, it just stayed there because now all that water started to turn to steam. It started to boil. And that requires a certain amount of latent heat too. So the temperature doesn't change in that phase transition. Once again, it's going from one phase to the next, so that requires energy. So what we want to do is we want to figure out how much total heat was added to this water. And we can use these two equations here. This is Q equals mL, which is heat, is Q, equals mass, is M, times latent heat for any phase change. So here and here we can use that equation. And then when the temperature changes, we can use the other equation for heat, which is Q equals mc delta T, where M is still the mass, C is the specific heat capacity of water in this case, and delta T is a change in temperature. So let's do that real quick. Let's find out how much heat it took to melt that ice. Well, let's plug in the numbers. So Q is the amount of heat, energy, in joules, equals mass. Now the mass was 58 grams. We have to convert that to kilograms, so that's 0.058. 0.058 kilograms. Now the latent heat for ice is 334,000 joules of energy per kilogram of ice. So 334,000 joules per kilogram. Simply multiply those together, we can get our latent heat of fusion for ice. When I do that, I get a value of 19,372 newtons, joules. Right. So this is 19,372 joules of energy to take that ice and melt it to water. Now I want to figure out how much energy it takes to go from 0 degrees Celsius water to 100 degrees Celsius water. And that equation I have to use is Q equals mc delta T. So what I use is Q equals m, so the mass of the water was 0.058, multiplied by C. Now the specific heat of water is 4,184 joules per kilogram Kelvin. 4184. And the temperature change of the water, it went from 0 degrees Celsius to 100 degrees Celsius. The temperature change is 100. Now technically we should measure temperature change in Kelvin because temperature is measured in Kelvin, but Kelvin and Celsius have the same scale. This would be 273 Kelvin, and this is 373 Kelvin. Same temperature difference. So temperature change is 100. So we multiply those together and figure out how much heat it takes to raise the temperature of the water. And that ends up being 24,267 joules. 24,267 joules. Now, if I want to figure out how much heat it takes to boil all the water, I would use Q equals mL again. So I would use Q equals m times L, where the mass of all the water would be 0.058, and the latent heat of vaporization, so basically latent heat of steam, is a really big number. Latent heat for steam is 227, let me check here, 2257, 000 joules per kilogram. Huge number. So we multiply those numbers together and we get that heat for boiling the water. But I'm actually not going to do that. Because if you noticed at the end of that lab we just did, there was still water left in the container. So I did not boil all the water off. I only boiled some of it off. And I could measure how much mass that I boiled off by measuring the difference of mass, but I actually did that and I actually didn't boil that much water off. So I don't know that value. I'm going to leave that blank, but it doesn't matter. I don't need to know that value. I can just end it right here. I can end my graph right here. So I'm going to figure out how much heat it takes to melt the ice and raise that ice or water temperature to 100 degrees. And all I have to do is add this amount of heat energy to this amount of heat energy. So when I add this number to this number, I get a total amount of heat energy to that point right there. of 43,639 joules. 43,639 joules. That's how much energy it took to start with ice and get it to steam. Not boil all the steam away, but just get it to that point where it starts to boil. That's how much energy it took. Okay, so here's my final numbers that I have to work with. The amount of heat energy it took to get that ice to start to boil, the total amount it took was 43,639 joules of energy, of heat energy. The amount of time it took to get there was 754 seconds. Now, the reason I don't use 1,000 seconds is because I left that last part off where we started boiling it, because I don't know how much I boiled off. So at 754 seconds is just to get to the point where it started to boil, and that's the value I'm going to use. Remember, I measured the current of the kilowatt of the hot plate was 1.97 amps, and the voltage used was 120.8 volts. And what I want to do is I want to find out the efficiency of this hot plate. Now, if I were to write a conservation of energy equation, here's what it would look like. I started with electrical energy. So I started with electrical energy, EE, and then all of that electrical energy went to thermal energy, heat, Q. But, just like thermodynamics, every single time you go from one type of energy to another type of energy, there's always going to be dissipated energy as a product. You're always going to lose some in that process to the environment. So that's ED. That's bad. Typically, we want to reduce that value. Now, another way to think about this is to write a ratio. What's your useful energy, your product, over your initial starting energy? So the equation for efficiency is labeled as N. Don't get that confused with number of moles, because it's also labeled as N. Efficiency equals the useful, or your ending energy, over your total energy. Now, it doesn't have to be energy. It could be power as well. It's useful power over total power. That also works. Let's see what we got here. I know my total power. My total power is just I times V, because P equals IV for electricity. I take I times V, and I get a total power of 238 watts. If I take 1.97 times 120.8, I get a total power. I get a total power of 238 watts. 238 watts. Now my useful power, well, I have my useful energy, and I have the amount of time it took to get to that amount of energy. Now, if you remember, power is just energy divided by time. It's how quickly you use the energy. So I literally have to just take this number, divide by 754 seconds, and it's in the right units, because joules per second is the same thing as a watt. So I take 43,639 joules, divide by 754 seconds. And when I do that, I get a power output, or useful power, of 58 watts. So now to figure out my efficiency, it's going to be a ratio of these two powers or energies. I take 58 over 238, and I get a decimal number of 0.24. That just means that 24% of my energy or power was useful, meaning that 24% of my electrical energy that I put in actually heated the water. Where did the other 76% go? Well, it went to dissipated energy, friction, heat. Wait a second. I thought we just calculated heat. Well, maybe it went into heating other things like the glass or the air or the surroundings or the wires in the cable, the cord that connected the devices. Maybe it was sound. You heard it. You heard some sound there. Maybe it was light energy. There's lots of different types of energy that was released that we can't use. Dissipated energy is just like non-useful energy. Closing thoughts. This lab or activity utilized a couple different thermodynamic concepts. Conservation of energy, first law of thermodynamics. It utilized specific and latent heat ideas, how to calculate total amount of heat, Q equals ml, Q equals FC delta T. It utilized the second law of thermodynamics, where you dissipate energy along the way, and we can calculate an efficiency of that. It also utilized the third law of thermodynamics, where temperature is directly proportional, or essentially temperature is average kinetic energy of the molecules, which is why when you have a phase change, the temperature doesn't change because the kinetic energy of the molecules is not changing. All the energy is going to breaking the bonds of the molecules. So it utilizes the 3 laws of thermodynamics. It utilizes specific and latent heat, and it utilizes real-world application of how to calculate an efficiency of like your stove or hot plate or of a fire or whatever it is you're using to heat up a certain material. So hopefully that all makes sense. Hopefully the lab goes smoothly for you, and hopefully it's a hot topic. Take care.